average home, and then you're looking at that would be the dark colored one. That's the national average, and this is basically space heating now for the now house. And then as we go along, we get water heating and appliances, and then space cooling. So that's energy. Oops, sorry. That's energy consumption. But now if you look on this side of the line, now this is on the annual renewable energy. So the grid connected to solar photovoltaics is producing this. And then we also have hot water solar. And then there's also the gray water heat recovery I mentioned earlier. So now if you look at this little box here, national total energy profile, and then we have the R2000, and now this is the Now House, but the only one of them all that has renewable energy is the Now House, so it's producing this, and in the end it comes out to almost a flat line. Now that sweet spot of that flat line, that's where everybody really wants to try to achieve. If you get it over top of that, even better, because then now you've got net zero plus. So this is what it looks like on the south side, of course. Photovoltaics and hot water, and what it looks like in the front. I mentioned earlier, if I had time, I'd talk a little bit about what's going on in the north. Now, they weren't able to get any equilibrium projects built in the north. However, our researchers have been working closely with a lot of the communities up there to come up with solutions to their problems, of course, of healthy housing, a lot of issues with indoor air quality, asthma, people being sick in unhealthy houses, and also super cold and again, energy pigs. And the cost of fuel for heating up there is extremely expensive. So they have to come up with some other answers. So if they're going to build new construction, what do they need to do? What actually, the Yukon Housing, especially even taking advantage of visiting some of the equilibrium projects and having fantastic staff, and I guess one of the things that really helps a lot is being able to quickly adapt to some of these new concepts without having too much resistance from government and locals and so on. They've decided that this will be a design in which they're going to incorporate and they're going to raise the bar to this standard, and they call this their super green home. And I think, honestly, they're probably one of the most advanced in the country, I have to admit. And of course, in that area, I mean, when you're looking at most of the homes being heated with oil, they have to have different, they need an answer to their problems, because people are spending sometimes $1,500, $2,000 a month in the cold winter times. And they just can't afford it. When you look at housing affordability, I mean, that is atrocious. So what they've done here with their super green home, they've adopted the double wall construction. I think they've even gone beyond that. They did an excellent job with this. When you look at a floor design on this one, right in the far end, hopefully you can see that from back there, what it is the floor joist system actually sits on the inside of the basement wall section. Now, this is a pressure-treated foundation in this one, and on a crawl space. So this could be done either in a basement or a crawl space design, depending upon how far down you want to go. But what happens is that the floor joist sits on the top of the interior partition, and what it allows is for your installation to continue all the way through. So you have now a nice complete blanket, because this is a really bad area for air leakage in these areas. Let me move back, sorry. Pushing the wrong area. In that whole area where your floor joist goes all the way through to the outside. So if you can actually button that up, and there's no option for any air leakage in that area, and they blow in cellulose insulation right from the bottom all the way up. And so it's basically, it works really well. So it's a balloon style cellulose insulated blanket. It wraps completely around the exterior, the inside walls, and the floors. But not cellulose in the floors, of course. It utilizes a setting replacement designed to self-fill settlement voids in the blown-in wall insulation, eliminates most of the thermal transfer or the heat loss through the framing materials at the bridge between the warm and the cold surface of the wall. So it's really comfortable. It reduces the air leakage through the wall, the ceiling, also in the floor junctions. It's really quiet. It reduces outside noise transfer. It's very economical, so pre-manufactured wall studs provide quicker framing than the other double wall designs. So the floor systems are actually, floor systems and the above ground systems are all pre-manufactured, and so it goes really quickly, and it works well. Oops. We've also done other projects too in the north, in Arviat and Qaluit and many others. And some of the processes that CMHC's done is just to not walk into communities and say, "Oh, we're just going to build this whether you like it or not." Too many houses on First Nations, for example, has been pretty much just front-end loaded over the years, and we want to ensure though that whatever was going to be built was going to be built right, and not only for them, but I mean, the idea is for the community and respecting the community, what they want, and also to respect our culture. And what we've done is we hosted design charrettes in the community and had elders, children, everybody, and all the decision makers, all of the charrettes, and to help with the process of what do they want to see in their housing. And I don't have any slides of this, but it's really kind of interesting. I'm just going to quickly tell the stories that when we had them come in, it was really interesting because the women said, we really want a nice place that we can actually do some of our sewing and work with the skins. And of course, you know, the guys wanted some place that they can actually do their butchering and skinning their seals and working on their furs. But on the other hand, though, too, is that most of their clothing for outside is seal skin, and you can't store that indoors. The skin will rot and the fur will fall off. It needs to be placed in cool storage areas. So what they came up with is actually, when you walk into the house, first of all, you come into sort of a vestibule area as a windbreak, because of course you get tons of winds up there. And as you walk in, there's a cold area where on one side it's sort of a setup where they can actually do their skinning and their butchering right there in the house. But it's actually not part of the house, sorry, because you have to walk into another door and then you're actually right into the house part of it. But at least the ladies there, they have a sink and they have areas that they can do their sewing. So it's their shop. Also the guys kind of have their shop. And it's not extremely huge. But instead of bringing this right into their living room like they ended up having to do and causing all kinds of problems, they actually have sort of their little designated work areas, which work really well. When you walk into the house, it's a big open area. And the bedroom doors are actually just opening straight into the living area. Because the way they live is they like the idea of everybody being all together in one room. So in respecting all of that, they can eat, they can, in the yard or the kitchen, most times they actually sit right in the middle and eat. They were putting just cardboard on the floor and putting their food down and then just sitting in a circle eating away. And so they allowed a big area for everyone to actually meet and eat. Of course, with technology going on today, who's without internet? Who's without using computers? Well, instead of children going off and hiding into their bedrooms with computers, they actually have like a little area, and so that they could work on their computers, but still be part of the social mix within the house, within the family. They felt hallways are just a waste of floor space. Why bother with hallways? That just takes an extra 3.5 feet of your floor space. So this way here, they eliminated the hallways altogether. They were happy with that. And I think it was in Qaluit, yeah, where ships only come in at certain times of the year. Otherwise, I think it was in Arviat, where the storage, the ships come in only at certain times a year, where they can only purchase certain types of foods, canned product, and everything else. So can you imagine that we have it so good where you can go to the store, once a week, you can do all your major shopping and so on, and you come home and you consume your goods, and you keep doing that on a weekly, bi-weekly basis or daily basis, whichever you choose. But they don't have much choice. They basically will end up doing their major shopping once a year. Well, guess what? They need their own little storage area. So they need a storage area in their places that they can actually put their cans of food and other types of perishables, I guess, and store that, because it's going to take a long time before they can do some more shopping. So they needed an extra space for that. And of course, you look at building design, building it right, building it with passive solar, and using these advantages of some of the technologies that we're all learning from here, incorporating that in there. We're able to come up with some neat, really great design that community folks just love, and it's been working really, really well. So on that note, though, something I want to mention, I know it has nothing to do so much with energy efficiency, but it is something, when you're looking at affordability, that we would like to ensure that we try to incorporate in the floor plans and the design of the homes. And what that is, we call it flex housing, and it's just a CMHC trademark. However, out there you can call it universal design. The very small portion of this is basically being, recognized through visitability, but that's very limited. So I just want to quickly touch base on some of the features of what we like to see and incorporated when you're looking at accessibility and incorporating these floor plans. Some builders will actually specify that this subdivision or community developers actually incorporate that in the requirements for builders to try to best design their homes using some of these features. And for example, this one here, if you look at the very top, you see accessibility of a sort of a level threshold. Now, this is good from stroller to the roller at the end, in case you're in a wheelchair eventually. So it doesn't really matter in the end. You can have the integrity of living in your home as long as you possibly can. We know when we're looking at about aging in place, this is really important. And if the homes are not designed this way, then guess what? Communities now are responsible then, and not responsible, but they're struggling in the end to try to come up with other alternative housing types for aging seniors. And of course, we know where that's going to look like in another 20 years from now. We're not hiding the fact that all of us are getting a little older, and we have fantastic, wonderful students here that are going to look after all of us, once we're all going to be needing wheelchairs and stuff like that. But the idea, though, is that if you actually build your house right and you incorporate some of these ideas, you're not going to have to spend all this money to put in these big, ugly ramps, and they cost a lot of money. So if for instance, going back to community design, that if you're going to go in an area subdivision, that the designers take into consideration all the different slopes that you're going to need for proper surface drainage, of course, but also to allow that the landscaping can actually slope it towards the level of your threshold. So they're not ugly, so it looks natural. Your sidewalk actually goes right level to your doorstep. It's all part of planning, and understanding these design features, that these things should, and I say they must be incorporated in a floor design. Trevor could probably touch a little bit on that in your home, because he did a fantastic job with that idea. Accessible switches and outlets. Now we see a little guy. Well, that's great for the little guy. But then the thing is, imagine yourself in a wheelchair having to reach way up to adjust the temperature in your home, or reach for switches. Actually, what we say is, lower the switches, raise the plugs, even the windows, if they're down a little lower, so that way you can easily reach the mechanics of the window for operability. Lever-type door handles, not only entrance doors, interior doors, your closet doors, your cabinet doors, using more of a D-type handle instead of these little round things where eventually you have a hard time grabbing onto. And also in the walls, you'll see that before you drywall, it's easy enough to put some plywood backing or just knock in some 2x4 backing, where eventually you'll need some good reinforcing for putting on grab bars and so on. Right at the time in the planning and putting this in really doesn't cost hardly any money. But then if you're needing later on down the road to go and rip open the walls to put in your backing, because now you need some reinforcing to put in your grab bars, that's going to cost a lot more money. So if you think ahead, you put these in, it really doesn't add a lot of money to that. This is just an example of a kitchen, where you'll see where the stove area is. It's hollow underneath there. Well, we're not trying to say the house should be designed to look like a hospital, but in this case here, they could actually design it in such a way where there's doors that go underneath that the stove area, and you don't need to have like an entire box. That the countertop goes right over the top of that whole area, where you can open those doors and you can slide a wheelchair underneath there. But it's a lot easier to keep clean, because usually what happens when what's usually underneath say a kitchen sink or stove, or well, not really stove, but a kitchen sink area, you mostly keep your garbage in there, you keep all your cleaning chemicals and all that other stinky stuff into there. So if you look at the oven, actually it's not that easy to find, but I think it's a smart idea, is the door. Look at the way it opens. So imagine yourself in a wheelchair on a conventional oven, having to reach over It's already tough enough as it is as a person that's willing and able that you can do so, but to reach over top of a hot oven door. But this way here, you pull out the little shelf, pull out your roast, open it up, you put it on that shelf, baste your roast, put it back in, safe, easy. So you're going to look at some of these different features. There's tons of other features, and here again, you get more information on our website about that. I'm just touching on a few things. But we're looking at adaptability as well. In this case over here, you'll see that you have a washer and a dryer in your sort of main washroom area or your mudroom area. However, later on, if you want to convert that to a roll-in shower, well, you can relocate your washer and dryer easy enough. And then this already has it built into the floor drain. And now you already have your hot and your cold water running into there, and your drain is in the floor. So you can actually set this up as a roll-in shower. Easy. What does it cost? Otherwise, if you didn't do this, you'd be into the thousands of dollars to modify your home later on down the road. But here again, it's easy. You're looking at a room space. Right now, for instance, you see on this photo, is that you have like a little office space, and you also have a bedroom. I'll show you this other one. This could be the other way. You can have this big office space, and go the other way to say, well, if you had an extra child and you say, hey, I need another bedroom, the way you've already pre-designed it is, of course, we know by the code you need a means of egress, so you have your window placements and your plug placements and everything else. Well, in this case here, you want to split this up into 2 rooms. All you got to do is just basically put in a frame in between, drywall it, and that's it. You've already met your means of egress. You've already met your power. And you actually have already in one area before you drywall it, roughed in a rough opening for a door. So now all you got to do is just take your keyhole saw, cut out the hole for your drywall, and you already have your rough opening, and pop in your door, and Bob's your uncle. You got your room, and that's it. And so if you think about these things and incorporate that in your floor plans, away you go. We're looking at a few different types of flex houses that were built, and there's no limit. By adding granny suites and so on, of course, you got to ensure that everything complies to the zoning bylaws. But we're looking at even in apartments, like this is University Flex condos in Burnaby, BC. They took 2 units into one. They made different types of units. This one here is sort of in Edmonton. It's a flex condo, so 2 units in one. But what they've done is they sort of shared the space of living and kitchen. This was a slide that I actually thought I'd add in regards to cost feasibility. This is I was able to get this from Jurgen Korn from Yukon Housing, and just to kind of show about about how they calculate the affordability factor of these units, because the big challenge is to say, well, it's nice to say I'm going to build an equilibrium house, but it's going to cost too much money. Well, what they were able to do here is to show. If you look at number 1, that is just the standard construction house, and then you have the standard enhanced house 2x6 or 2x3 framing. Then you have the green home, which is more like an Arcturus 2000 sort of, and then after that there's the super green home. And if you look at this line right here, this is your base cost. This is how much more it costs than a conventional home. And in the bottom line here, it shows here $24,000. So it costs them roughly $24,000 more to build a super green home. Think about this. You don't need all that extra floor space for all the big heat plants anymore, because what they're doing is they're basically using just electric baseboard heat, and they don't need lots of it. And of course, every one of them will have an HRV. But to thicken the walls, to add the insulation, the heat system is not as elaborate as needed, so you save some money in that end. So it's $24,000. And then now if you look at what your yearly heating load. In this corner, there's too much of an angle. In this column here, you're looking at, say, over $3,000 in yearly heating costs and fuel costs. And then, and by the time you're done here, it's $651 a day super green home. So if you basically look at averaging this thing out, when you're looking at your principal and your interest and your mortgage, on that yellow column, you'll see from $240,000 at the top down to $264,000. And so your principal and interest on that loan, I think I have it on the next slide here, sorry. There we go. In this column, you'll see the principal and interest is from $1,333. It goes up to $1,466. And you say, well, wait a minute now, that's not any cheaper. That's more money. However, if you basically look at what the net payments are after you've actually calculated your energy, it's actually $74 less to live in a super green home than it is in a conventional home. So it makes financial sense. You can do it. And the thing is that they did not necessarily go with all kinds of photovoltaics and solar hot water. They didn't add all that. What they really concentrated on is a really good, super tight building envelope, and also taking advantage of passive solar energy. And that's basically keeping it simple. And it's solar ready if they need to. So that's pretty much it for my presentation. I think I got about 2 minutes here if I have any questions. And I already have an arm up there. Yes?
I'm glad you ended up with a cost comparison question, because that's what I wanted to raise. Great presentation. The Now house, we probably got at least 100, maybe closer to 200 four-time houses. And so the cost comparison in terms of per square foot, because it's a smaller house, between that house and the demonstration houses that we built, what's the construction cost comparison of retrofit versus starting?
It's a good question, and I don't have the actual figures, but what I could say right now is I think by the time they were said and done with doing the retrofit of the house, I think it came in closer to around $80,000 or $85,000. Now it sounds like a fair chunk of change, just considering it's retrofitting an existing house, but this house will now last many more years, probably longer than the 60 years it's already lived, and it'll go on, and you look at the long-term operational costs. So I know I don't have the answer to the actual figure on like this one here as to what your PIT will be at the end, but you know, what's the average housing cost? And if you put in $80,000 into the home, you're definitely going to be recovering that. Yeah, I mean, it'll take a little longer, but if you tag on $80,000 to say, like, what's the average? What would you say the average cost of one of those houses on the market right now? The way they sit. Yeah. About 120. Well, 220. Okay, so 220, and let's just say, you know, comes down at $300,000 total cost by including that in. You know, I mean, over a 25-year period, you're definitely going to get all your costs back, and you're going to be living in a much healthier and more comfortable home. Yes.
4 times anywhere from 140 to 160.
In there?
Yeah.
Okay. Okay.
Question about the Now house as well. I heard a story in a previous presentation about they had to change the wall system in front of the house due to some regulations. Do you know anything about that?
To what type of regulations, sir?
I heard there was some building setback regulations, and the city of Toronto wouldn't let them build out from the house. Is that? Do you know anything about that?
No, sorry, I don't know. Okay. Yeah, go ahead. Yes.
Are you answering him, or are you?
No, not for you there. I'll get Philip in a second, but I think Philip might have some to say about that. But go ahead. Yes.
With these houses, is there always some form of air exchange involved? Because you're building such a tight house. My concern would be in that you might end up with sick air syndrome.
Oh, absolutely. That's a very good question, a very good concern. As I mentioned, like every one of these all have an HRV. They all have a heat recovery ventilator system, and they will definitely not work if you don't have them. It's a critical point. I mean, you just cannot expect to be building a super airtight envelope and putting people in a plastic bubble and expecting them to survive. It's not going to happen. I mean, you will definitely have a lot of mold issues and so on. You have to have good fresh air in. You also have to have the warm, moist, stale air exhausting. It's critical. And the only efficient way of doing so is by using a heat recovery ventilator. To add to that, I didn't mention it, but the urban ecology project in Winnipeg, they thought they'd even try something a little different. They actually put in 2 HRVs in running in sync to each other. And so the idea is the first HRV is running at a little over 75% efficient. Right? That's the way it's working. And they basically figured that once they add the second HRV, it's going to take 75% efficiency of the 75% efficiency of the first unit. So in the end, it should be coming, their calculation is roughly about 95% efficient by running 2 HRVs in line. So that's another thing that we're actually learning on. We'll find out how that's going to turn out. But this way here, you're still going to be able to recover most of that heat going out by and still bringing in some good fresh air circulating through the house. At the same time, it's exhausting. So this way here, we won't have any mold issues. We're going to have some good fresh air throughout the house. Phil?
I just trying to respond to this gentleman's question because I came from Toronto. I also live in Toronto myself. They do have a certain requirement for setback, especially on the side, doing a small but I think you can go through a variance application, and if you have support from the community, most likely you will get it because it was kind of precondition, and you're doing something good for the community. So my personal experience is that, well, in Toronto, those houses would easily cost 400,000 in the real estate market compared to here. So there's a differential. So, but still, it's important to work out the business plan to make sure you can kind of have a reasonable payback period before you jump into that direction.
Thank you. Thank you. Yes?
Have you done any that are based on geothermal heat?
The Chess home in Red Deer is on geothermal. However, I haven't got any data yet from that. I have to maybe add in a little comment on that one, though, is that I know we just did another workshop similar to this at the University of Manitoba just on Tuesday, and some of the designers that we were involved in the Riverdale project, also in the Winnipeg project, both agree to the fact that you say you look at the economies on whether or not these things are really worth installing. And what we're really already seeing, without waiting for the final report of everything, is when does it actually come to a point where it's actually effectively going to operate? Well, not effectively operate, but when is it actually going to be financially feasible for this? Because if you look at how much energy, if you build it right and you build a good building envelope, you take advantage of passive solar energy, it's good and tight, you really don't need a lot of energy to heat these houses. You really don't. So although geothermal sounds like a really nice, sexy word out there, it doesn't necessarily mean that it's really feasible. It works. I mean, they work well for heating and cooling, but it's like if you want to take one of these homes that are out there, like the big mansions, say, oh, I'm going to put in a geothermal system because it's going to be way cheaper than doing a complete retrofit and so on. It's like feeding a Hummer. The thing is that that might be a quick, easy fix for these big leaky sieves, just to pump in more cheap energy to keep them heated. But the thing is that when you're going to be building a brand new house that's really going to hardly need much of a heat plant whatsoever, when it's going to cost you $20,000 or $30,000 for a system like that, sometimes it just really doesn't make any sense. They are great, they do work well, but you got to ask yourself, if you're willing to do so as a homeowner and you want to put that in, go for it. But if you're really looking at the bottom line, it probably wouldn't be that feasible for only a single unit.
Would it make sense for an entire subdivision?
That is difficult to tell. Geothermal, if you're based in Moose Jaw, absolutely. I mean, I'm sure you probably have done the studies of what you already have. You have a gold mine sitting under that ground right now. You have a gold mine sitting in the ground.
I don't have to say anymore more, because that was what I wanted you to say.
Oh,
Okay, you just stop on that for
okay, before I put my foot in my mouth, I'll stop right there. Oh, I just, when I first heard of this, you know, and I'm staying over at the Temple Gardens, and I just, before even coming here, I had to go see, smell, feel that spa. And it's awesome, and I'm going, man, I wish I had this in my community. You know, it really, it's amazing, and I strongly believe that you have to take advantage. On that end of it, what's it costing? It's you must, and we'll continue to reinforce that as we go through. And that's another great reason why, you know, we got Philip to come in from Toronto, even talk about what they have out there to look at how we can encourage you guys to carry on with that thought and that dream and make it happen. Yes.
Red Deer gets a lot of hail. How do your PV panels stand up to the hail?
I'm sorry, the what?
Red Deer gets a lot of hail. How do your photovoltaic panels stand up to hail?
Extremely well. I don't have all the figures, but actually that was a question that was asked to Gordon Howell, which is the PV expert of the Riverdale project. And well, when they manufacture these photovoltaic panels, it has to withstand huge tests. And I think what it was that they use, don't quote me on this, but they use metal like ball bearings that are shot at them like 50 kilometers an hour or something like this, just to ensure that these things will withstand all that, like the weight and the power and the impact. So they do go through substantial tests, and they have to be very strong. So I don't think there'd be any problems, from what I understand. Yes.
Curious how much more a homeowner, a prospective homeowner, would pay for a house. I'll turn it around from a builder's perspective or a developer's perspective. They want to put a box up that they're going to sell. How much more is the average consumer prepared to pay to buy a standard built home now versus a home with many more of these features? How attractive is it?
Yeah,
It maybe doesn't make economic sense up front, but there's a certain amount of the population is interested in moving this way regardless.
You're right, and I can't answer the question how much more they're willing to pay, but I can tell you that they're very interested in it. Before we even started this whole thing, it used to be called Net Zero Healthy Housing before we came up with the name of Equilibrium. Before we got everything started, we did focus group surveys right across Canada, from the north and right across Canada, to determine just exactly what the marketability would be, these in different aspects. And sort of to cut to the chase, people were really interested in this, and because of environmental advantages, but also in comfort and health, in comparison to what's out there. And if they have the choices, they're willing to pay more money. And now, and of course, the big obstacle was, like, oh, it's going to cost more. Well, here again, if you look at R2000, and that started back in the early 80s, well, one of their biggest challenges were to convince people to increase the insulation, to make it more airtight. What are we saying today? You know, it's taken so many years for R2000 to almost become a household name. It's taken forever, a long time, way too long. We're at a crunch right now. We're at a crunch that the energy is going up, and it's not only going up today, it's going to continue to go up. And we got to make those changes. And the thing is you know, they're at this point in time, they realize that we want to be comfortable, and we want to also save some money over in the future. So if they could see the light, and consumers are a lot more intelligent these days. They're really catching on to where we're going at with housing. That they are a lot more willing today than they have been, 20, 25 years ago, to grasp the whole idea of what we're really going at with this. So, for instance, I mean, I'd like to redevelop a new slide of our own once we get more data instead of using Yukon Housings. I really appreciate Jürgen Korn's spreadsheet. But we will still be able to come up and say, look, at the end, if you did this is what it's going to cost. You know, it's going back to the question of geothermal. Now, geothermal, you have it here in the ground; it's already heated. You don't have to use up any energy except for pumping and pushing it. If you're going to be doing geothermal in a house, a single-family house all by itself, by using a well system, or if it's going to be ground loop system, whichever system, costs a lot of money. So you say, well, how can you make that affordable? well, maybe if you really want to push that system, maybe you might want to do a small cluster. Maybe, you know, 3, 4, 5, or 6 houses can share that system, because there's no reason why it can't, you know. But that adds a lot more. So where do you find that sweet spot in costs? So when the homes are being designed, there is a formula that you can use to determine how far you're going to go. How far are you going to go with insulation before it comes to the point of no return? How far are you going to go with all these costs added into it before it comes to the point of no return? So you build your house to that specification and get a full maximum return on your investment. And this way here, the homeowner will be able to say, well, I don't mind spending extra $20,000, $30,000, $40,000. And then believe me, in some of these houses, of course, it's more than that. Yukon Housing was actually able to find that sweet spot in their design to say, yeah, $24,000 for that specific model, and that's where they stop. So the builders have got to look beyond just say, well, I'm going to build it a little bit thicker, and I think that's going to work. You don't have to think. You can actually calculate it based on measurements and construct in such a way that you can price it so that it will be marketable.
We better stop you there,
Yeah.
Jeff, because Trevor's supposed to start in 1 minute.
Yeah, I know. Okay, guys. Let's have a 10-minute coffee break then, and we'll get back here. Thank you. Thanks for stopping.
Anybody?
Had a chance to take a break. The next speaker is Trevor Gamlin. Oh, but before I do that, Trevor, I got to ask a question of the second semester students, because we toured Gangnail Trust yesterday in Pilot Butte, and I want you to think about the realistic issues of the numbers that Cam just talked about. When we talk about our typical ceiling attic insulation of an R40 or an RSI 7.0 compared to what we're doing in these super insulated homes, R65 or an R80, and you think about the trusses that we just saw, imagine how important it is now not to compress that insulation at the heel. So we would have to go to a much higher heel, and I know that's a technical thing I'm talking about, but something that's very vivid to the second semester architecture students from yesterday, and it has to be understood in the detail. But anyway, I don't want to take up all the time here. Trevor Gamlin is the operations manager and partner of the Avalon Homes Central Alberta Division. He's been involved extensively in the sustainable building industry for the past 8 years. In addition to acting as program manager on the first 3 homes in Avalon's innovative Discovery Home series. Trevor was an officer on the board of directors for the Built Green Society of Canada board from 2006 to 2011, as well as co-chair of the Standards Committee and lead technical advisor for the Built Green program. His passion is for the improvement of the overall building science and realistic, economical, attainable solutions in sustainable building. So, without any further ado, I introduce Trevor Gamlin.
Okay, first off, I'm going to sort of apologize to Cam, because a lot of what I'm going to say up here is sort of directly flies in the face of some of the stuff he said, but we got to keep in mind that the Equilibrium project was something to discover and learn things, and we did learn a lot, and it was a lot of it was different than what we thought it would be. So, moving on. So yeah, I'm an operations manager for a small to medium-sized home building company in Alberta. There's actually 2 companies. We're sort of sister companies, and we work with each other. I'm out of Red Deer, and our sister company's out of Calgary. The home I'll be focusing on mostly today that was in the EQ program was done in Red Deer, as our first 3 were. What we decided in about 2004 as a company, we're a fairly young company. We took over from the first generation that founded the company in the 80s, and sort of we're the second generation, is that we wanted to do something pretty progressive. So about, like I said, 8 years ago now, we decided that by 2015, what we wanted to do was to do all of our homes as net zero homes by the year 2015. But we wanted to do it at no additional cost to our customers, and that was the integral part of that. Seemed like a pretty good idea at the time, but now we're about 3 years away, and it's getting a little bit closer to crunch time, so I'll fill you in later on how close we're getting to that goal. So we, to get us closer to that goal, we came up with what we call our Discovery series of homes, where every couple of years what we do is a Discovery home. We'd move closer and closer towards that goal of net zero, as well as trying to realize the cost of doing that and the best way to do that efficiently. So most of my presentation today is going to be sort of that journey, and then mostly I'm going to focus on Discovery 3 because that's the one at this point that we've learned the most from. We're just finishing our 5th one right now, but with Discovery 3 we've had 2 to 3 years to monitor it since the homeowners have moved in, so we have some real life data, and that's kind of where what I say is going to diverge from what Cam had to say probably. So moving on. Okay, so I already talked about what the homes are and why we started doing them. So our vision, of course, is to build all the homes by 2015. Went through that. For our purposes, we define net zero as achieving equivalent energy rating of 100, which means, of course, that the home is going to produce at least as much energy as it consumes in a year. I'll talk about that a bit more at the end, but you'll see that there's various definitions of net zero, and that's one of the things as an industry we kind of need to come together on and come to a firm definition on. Our first one that we did was in 2004, like I said. It was our first attempt at moving away from conventional housing. Prior to that, we did pretty much basic conventional housing. I'd say industry standard. We did win a lot of service awards, so we did focus on building science and stuff, but as far as the specifications and the energy efficiency and the sustainability, all that stuff, it was, I would say, pretty close to industry standard at that point in time. I already talked about our newest Discovery 5 home that's just being finished in Calgary now. We'll get to that. Okay, I'm not sure how well everybody here understands how the energized system actually works, but 100 basically is the target, meaning that you would be that flat line that Cam showed earlier where you're going to put out as much energy as you consume. And by energy, of course, you have to not just factor in natural gas, but also electricity, water, all that stuff, all the energy that actually goes into a home. As you can see by looking at that sort of sliding scale, you can kind of get from what the average was. It says 68 there, but this is an older chart. I can guarantee the industry's moved forward since then, and probably your average home today is probably pushing closer to 75 based on just updates to the building code. Nonetheless, you can get all the way close to 90 without getting into any actual energy production. That's a really tough target. Like I said, the average home today, even with the new building code, is probably somewhere around that 75 range. So our goal is to move us from that 75, 80 standard range all the way down to 100 eventually. Our first Discovery home, first one we did, it was our first kick at the can. And what we did is we basically just focused on reducing the energy consumption, and we did some stuff with indoor air quality, improvement to the building envelope. Basically, we did some really basic stuff with not a lot of cost increases, didn't do anything too fancy, just kind of feeling our way out. So with installation, we did an R50 installation in the ceiling, which is not a significant improvement over the standard. It's about 10 over the standard. We did do some rigid installation under the floor slab. That's not a standard. Nobody else was doing that. We did something different with our wall system. Instead of the traditional 2x6 walls and 16 inches on center with fiberglass band insulation, we did a 2x4 wall, but we did 2 inches of rigid insulation on the exterior of it. We did that instead of plywood, trying to, again, keep the costs in line. And we used some engineered bracing. And then we did, for the ceiling, we already talked about that. For the foundation walls, we also did R20 rigid insulation around the exterior of that. All of that maybe came to less than $5,000, which at the time was easy to hide in the cost, so to speak. Went from the industry standard of regular windows to a dual glaze with a low argon filling, nothing too weird there. For heating and ventilation, we took some big leaps from the standard. We went to a variable speed multi-stage furnace. We went to our first tankless water heater. We did our Venmar ERV. Cam briefly talked about what HRVs are. ERV is just another type of heat recovery ventilator. Just so everybody understands why those are so important, what they do is when a furnace runs or any forced air heat system runs, it does naturally have to bring in air from outside to heat up and then take the air from inside and put that outside. That's how you get the ventilation. It's not very efficient because when it's cold outside, which is when you're heating the air, you're heating minus 20, minus 30, whatever the air temperature is, all the way up to your room temperature. The way an HRV works is it forces that outgoing air through a heat exchanger first, causing it to take on the heat of the outgoing air, put it into the incoming air before it gets to your heating device, so that you're now heating air that might be, say, 10 or 15 degrees instead of minus 30. So that's how those work. And they do run independently of the furnace, even if you don't need heat. It has its own smaller fan on it, and that just makes sure that you're having that constant supply of fresh air. What an ERV does is it also retains the humidity that's in the air. It's just set up to collect that and put it back into the house, so you're not drying out the house, which can become an issue. We also had a UV air cleaner and an automatic exhaust fan in the attached garage. So nothing too crazy in that house. It's For appliances and lighting, we did just some Energy Star rated appliances, front-loaded laundry. At that time, we just did standard incandescent lights. CFL still weren't really big on the market. Did some motion sensors for some of the lights to reduce that electrical load. We focused a lot on air quality in that one. This was, again, we were sort of looking at a whole big picture. It wasn't just trying to get the energy efficiency down. It was focusing on the indoor air quality, the durability of the home, that kind of stuff. So we did some Liptus engineered hardwood. Liptus is just a kind of product that has a really fast growth cycle. I want to say it's 7 years, similar to bamboo. Comes out of South America. Did some indoor air quality certified carpet. Got rid of all VOCs, which are volatile organic compounds, and everything that we did in the home at that point. So eliminated all lacquers, all VOC containing adhesives, anything like that. We went with granite countertops, just because your regular laminate countertops are made out of particle board that have a lot of formaldehyde. Went with some low formaldehyde, new types of particle board, that kind of stuff. With that one, we went from the industry standard at the time of about 70 to about an 81 on the Energuide rating. We had an air change rate of 1.36. Now he was saying with the CEQ program they were targeting, I believe, 0.75. Is that what you're targeting? That's a really low number, just so everyone knows. The industry standard is probably, before this all became a big thing 10 years ago, was probably somewhere in the 7 to 8 range. And that's air changes per hour. That's how often the air in your home actually naturally gets changed out just through leaks. So 1.36 was a pretty aggressive target that we achieved. That was a picture of it. Looked pretty conventional. It's a pretty really basic plan. It was about a 1,400 square foot bungalow with a double attached garage. Nothing fancy, no big vaulted ceilings. Wanted to stay really basic. The original idea when we started this series was to continue building the same model of home for each step in the series, so that we could really monitor and see how we were improving and what the costs actually were. So you can see by the second one we completely abandoned that idea. On the second one, we incorporated a lot of what we did on the first one, but we did move into our first foray into renewable energies. It was the first non-subsidized net zero electricity home in Canada. It wasn't net zero energy, but it was net zero electricity. Did some gradual envelope improvements, similar to what we did in the first one, except we went with triple glazed windows, and instead of 2x4 walls, we went to 2x6 plus the rigid insulation on the exterior. Same thing below the slab, nothing too weird there. For the renewable energy systems, for the first one we did a 3.7 kilowatt PV system. Now I don't think Cam really went into the differences, but there are two kinds of solar renewable energy systems. One is PV, which is producing electricity, and the other one is solar thermal, which basically means you just take the heat from the sun and use it for heat. So you're just using it to heat stuff, and they're two totally different systems. So the 3.7 kilowatt PV system does, on a normal house, would probably do, of that size, would probably do approximately 30 to 40% of its electricity in a year. This house, we set it up so it would do all of it. We also had a 2-panel, which is like 2 4x8 panels. There were solar collectors with a 30-gallon storage tank, which just did solar thermal, which just heated water. That water we then ended up using for heating both the hot water for the house as well as some of the space heating. The way the space heating worked in that home is we got rid of the furnace entirely. We went with a fan coil, which is just like a furnace, but instead of using natural gas, it just uses hot water or some sort of hot fluid like a radiator to disperse the heat in the house. That way we're able to use some of that hot water from the solar thermal. We also did some radiant slab heating in the basement, tied that all into the solar thermal system, and that's what did all the space and water heating in the house. Ended up doing about 40 to 50% of the domestic hot water heating and not very much of the space heating. Again, the ventilation, pretty standard. We went with the heat recovery ventilator that was set up to do the humidity as well. One thing that we did try that was kind of novel there is we did 2 intakes for that. One thing with the ventilation is in the summer you still have to ventilate, but you don't necessarily want to bring in really, really hot air, because then you're looking at heating up the house and having to cool it. So we set up an intake in the summer that was on the northeast in the shade, and in the winter we built what's called a solar wall. I think Cam actually touched on a sort of a manufactured version of that earlier, but all it really is a big giant black metal wall that's designed to get really hot even in the winter. And we built that on the south side of the house, built a big air pocket behind it, did the air intake behind that so that we were bringing in heated air. In the winter it was already preheated before you had to preheat it, so adding some more efficiency there so that you didn't have to heat the air. For electrical consumption, we really wanted to focus on electricity in this one, so we got rid of as much electricity as possible, anything that needed heat. So went with a natural gas range, natural gas dryer. Basically, I'm going to get into more of this later, but anything that you need to heat, electricity is a very expensive way to do that. It takes a lot of electricity to heat things. So anything that needed heat, we tried to get rid of with natural gas. By then we went with the CFL bulbs. We did some imported dishwasher and appliances that were really ultra highly efficient. Did some motion activated lights, stuff like that. It was our first foray into water conservation as well. We did xeriscaping. For those of you who don't know what that is, it's basically a specific landscaping that's done so that you don't have to water it or irrigate it at all once it's taken root anyways. So you use drought tolerant plants, things like that. Did that for 100% of the exterior. It was a big corner lot, so that was quite extensive. Went with our first crack at dual flush toilets, did some ultra low flow faucets, stuff like that. Well, that one we got to an 88 Energuide rating, which was very impressive, and had a 2.35 air change rate, which is higher than our other one, but much more complicated house design. It was modified by level with some vaulted ceilings, things like that. Anytime you complicate the design, you definitely make it more difficult to get that air change rate down. Something I'll get into a bit more later as well. It's just a picture of the inside of the place there. You can see it's pretty kind of modern bi-level kind of design. The third one, this is the one that we're really going to focus on the most, that we've learned the most on. This is the one that we entered into the equilibrium contest. It was our third home. It was the first home in Canada to be Energuide rated 100. It was the first LEED Platinum home rated in Canada. And that one there, we disregarded cost entirely, basically. We just said, screw it, we want to be net zero, let's see what it costs. We just kind of threw caution to the wind. It was a good time in the market, too, you could do that. Backfired when we had to sell it, but we'll get to that. The sole goal is to get to that net zero status, so we did some really extreme, ultra high insulation values, some really large volume renewable energy systems. For the design, it was a modified slab on grade, so it was originally based on about a 1,500 square foot bungalow with an attached garage. And we did a lot of design charrettes, which are sort of, you get a whole bunch of experts together who don't agree on anything, and then you try to agree on stuff. So for whatever reason, we came to this idea of getting rid of the basement because there's some consensus among some of the experts that if you got rid of the basement, it would be more efficient because you wouldn't lose all that heat to the ground all winter. That, as we will see, totally backfired. So anyways, ended up being this combination bungalow, but we had to kind of go up to make up for the fact that we got rid of the basement, so it sort of ended up as this halfway between a bungalow and a two-story where we used the attic space as the second floor, but then we built knee walls to make it work, and probably should have just built it as a two-story at that point, but we didn't. For the envelope, we did structural insulated panels, which Cam touched on a little bit. Basically pre-manufactured panels. They're made with the polyurethane. They're pre-made. They come in a panel form. You engineer the house, you put them up, and they end up being your outside walls. Well, we did 2 layers of those because we thought we'd go really crazy. The second layer was just insulation. It had no structural stability whatsoever, just to get rid of any of that thermal bridging. Did that all the way around the outside. That was really cheap. R85 ceiling insulation. So that was we used 2 pounds of closed cell spray foam, the wall-tight eco stuff that you'll see Mike Holmes use on his program all the time. Same stuff. Went with R60, which was 12 inches of rigid insulation below the floor slab. I went with triple glazed windows, but instead of using argon, we went with Krypton, which has a little bit better of an insulation value. We used what's called Arctic brick mold, which basically means we moved the face of the glass from the outside where it traditionally is to the inside of the house, which looked pretty weird on that one because the walls were about 12 inches thick by the time we were done with them with that double sit panel, so the glass was really far on the inside. And then the other thing we did, which I think Cam touched on, was the exterior insulated roll-down shutters. They weren't actually automatic, but they were, you could operate them from the inside. Those turned out to be a really good idea. For the renewable energy, like I said, we just kind of said we want to meet our goal, so we went with an 8.3 kilowatt system with a double inverter for the PV, which is a very large system. I believe it was the largest one put onto a residential home at the time. Again, all of this is grid tied. And then we went with 165 square feet of collector panel for the solar thermal, and about 240 gallons of insulated storage capacity, so 240 gallons of insulated hot preheated water from the solar. 165 square feet of panels, turns out, I think there's a picture over here, and I'll show one here soon, but that's worked out to be about 8 or 9 panels. It's a lot of panel. One of the things that we focused on in this house before I move on is, like Cam pointed out, was to make it look really conventional. We didn't want it to look like the other entries in the competition. We wanted because our goal is to eventually produce all these homes as our standard homes and sell them at, you know, sort of traditional market pricing, one of the things that we've always been focused on is trying to make the homes look like almost any other home when you go down the street. So there's some things that we did to do that, and some of those things ended up costing a bit of money too. For space and water heating, we used because like he said, for the CMHC project, all the homes, we completely got rid of natural gas. Reasoning being at the time, you know, you can produce electricity, but it's not really something you want to do is produce natural gas in your house. So we kind of got rid of natural gas entirely. We had to make up for that. Very bad ideas I'll get into later, but anyways. So we went with this 3-phase electric tankless water heater, tied that into the solar thermal, so that's the backup. So when the solar thermal system can't keep up, you've got this tankless electric water heater. And what that does is it basically takes whatever the water temperature is and it fires it up to the temperature that you need, and that's going to be used for your domestic water, as well as in this house it was used for all the space heating. This house, the theory was that because we built it with so much insulation and tried to make it so airtight and did all these things that you wouldn't really need that much heat, so we didn't really put in a fan coil. We just did some radiant heat under the slab of the main floor. Didn't put any heat in upstairs, figuring that the heat would be trapped in that envelope. Again, not such a good idea. For ventilation, same idea, went with the HRV, but on this one went with the bigger one, and the other thing we did is we actually had them custom build and install an ECM motor for that one, because the HRVs normally don't have that. Some of you guys might know an ECM motor just runs a whole lot more efficiently, and it's got a variable speed on it. I don't know how well that works, but point is we knew it was going to be running a lot, just because it was the only air movement in the house. You don't have a furnace or a fan coil moving that air around, so we wanted to go really efficient with that, so it was using a lot of power. Also, it had some humidity and carbon dioxide sensors. Again, coming back to that concern that he brought up about making sure we had the house nice and healthy, the air quality was being maintained. Carbon dioxide's a great indicator of that, because it indicates that the air is getting stale, and as you breathe out, it indicates that need to refresh it. So that's how that was set up. As far as energy reduction, like I talked about, obviously got rid of the natural gas, went with the CFL bulbs, pretty standard at this point in time for us. The appliances, we did some wacky stuff. Got rid of the range and stuff entirely, went with this convection microwave / range oven. That was a piece of crap that didn't work, but we'll get into that. Also, we did, for laundry, they did with something that you sort of see more in RV laundry, where it's a combination washer-dryer. So the way that works is you throw in your clothes, washes it, spins it really, really well. It takes something like 6 to 7 hours to do a very small load of laundry. Hardly uses any power. And people moved in and got rid of that right away too. Water conservation, again, we did the zero escaping for 100% of the lot. Did the dual flush toilets. We did some ultra low flow automatic faucets. The high efficiency imported dishwasher again. And then for the first time we tried some gray water recycling units on our toilets, and that was just a really simple system. Those actually were pretty cool. They just basically took the gray water from the basins and then used that water for flushing your toilets. They're cool because they worked. They weren't cool because they were really loud, and the owner got rid of those too. Anyways, when we were setting down, we had a modeled Energuide rating of 100 with a 1.26 air change rate. Now that 1.26, again, not as aggressive as we were targeting. That's coming back to that design of getting rid of the basement. When we got rid of the basement, what we had to do to make up for that space was to build up and essentially build that sort of second floor. But we didn't want to build a second floor because that'd be way too easy, so we decided to make an attic-y second floor with like knee walls, and so you had a vaulted roof space in the center, and then you had these flat roof spaces on the ends, and you had to tie all that together, and you say 3 different roof lines, and trying to insulate that all and keep it from leaking turned out to be a challenge. As far as the finishes and such go, again, keep in mind the goals of the project being sustainability overall, not just the efficiency. We did a lot of recycled products. All the trim on the house, exterior and interior, all that stuff was all recycled from, I think it was like from grain elevators and schools, hotels, things like that were torn down. All the floor was 100% bamboo or recycled ceramic tile. Bamboo, again, one of those really fast-growing harvestable crops as far as hardwoods go. Quartz countertops, that was more to do with the air quality inside. Again, it's just a hard natural surface. Again, the zero VOC everything's. There's our guide to prove that we did what I said we did. That's our rating, our Energuide label. Those are all the verifications that we got on that home. The LEED Platinum, Equilibrium, or 2000, that kind of stuff. That's just a schematic of the photovoltaics. I won't focus on that. Like I was talking about earlier, we're really trying to tie the look into the house. So what we did was we sourced these open energy solar roof panels that actually look like sort of like clay tiles. As you can see by the finished picture and the one I'm going to show, it really ties in well, and at certain times you really can't tell that they're PV panels at all. So they're designed to be installed in conjunction with a specific kind of clay roof tile that goes around the edges and the other area that you don't use PV, which is a really cool idea. Looks really sharp. I really like it, but they're a lot more expensive than conventional PV, and also you got to upgrade your roof to these clay tiles, which are about 3 times more than a regular roof, and you've got to strap it out, as you see, which cost about 2 times what the roof is worth. And then what we had to do is we had to add trusses every 12 inches instead of 24 inches to hold the weight of all that, so doubled the cost of the trusses as well, so pretty cheap. There's kind of during the install process there. There's a close-up of how they look. We'll say one thing about PV, cost-wise we'll discuss that later, but it is kind of idiot-proof, which is nice. Once you have a PV system installed, there's really not a lot that can go wrong with it. We've yet to have a problem on any of the PV systems we've put in. Once they're installed, they work, they do what they say they're going to do exactly, and that part's actually quite nice. If you see down on the wall there, you'll see those other panels that we kind of put trim around to make it look like windows. It's also on another mudroom part of the house that you'll see in the whole facade. Again, we did that to preserve the look and make it look as less solar panel as possible. The other reason they're on the wall instead of roof, those are the solar thermal collectors. The primary reason for the solar thermal collectors, of course, was to heat the house as much as possible when you need to heat the houses in the winter. So one of the things that you're looking at is not heating it as much in the summer, because you're going to overheat, and heating it more in the winter when you need it. So when you put those on a wall, you're taking advantage as much as you can of the really low winter sun angle. And it just so happened this house was on a corner facing a street, so it worked out really well. We had really nice access to the sun coming right down there at that low angle. So that was all designed on purpose. And then the roof pitch was set up to actually take more advantage of the summer sun angle, which is a lot higher. Because we were grid tied, we wanted to produce as much electricity as possible to offset the electricity that we knew that we would pull off the grid. Sort of a fuller shot of the house and a little cross section of the solar thermal panel. The solar thermal panels, again, really simple technology. There's not much going on there. It's literally water or glycol, in this case glycol, going through copper lines behind metal plates that heat up with sort of a glass in front of them to protect them, as well as create more heat. Not a lot of crazy science going on there. They're super insulated to force all that heat into those pipes, and I can guarantee you from experience from doing this house and a few others, they get really hot. They do work. They get phenomenally hot, like ungodly high temperatures that you can't possibly use. It's a schematic of basically how those solar thermal panels worked. It really is, like I said, in theory quite simple. You run glycol through those panels, they get superheated, they go back to, in this case we had 220-gallon super insulated smart tanks that have heat exchangers in them. It goes through there, loses the heat to the water, goes back to the panels, so on and so forth forever until the tanks get to their maximum temperature. At which point, if you are still heating the glycol, then you have to dump that heat into the ground, just to make sure that you don't overheat the system. Dump the heat into the ground, of course you're running electric pumps to dump that heat into the ground, so that works out pretty good too. There's a picture of one of the tanks. Those are just the pumps that run the tanks. I guess I wanted to show a lot of pictures of the house. That's just a picture of what the house looked like when it was finished. So that's basically what we did on that house. I'm going to get back to why we should have done some of those things and the reasoning behind that. But first I'm just going to quickly go through what we did in Discovery 4 and 5. We haven't done any monitoring on those yet, and I'll sort of get into the reasons for those. So the first 3 were all done in Red Deer. It was all done by our company in Red Deer. The next 2 here that I'm going to talk about were done in Calgary. Both of them were done in conjunction with SAIT there, which I think is probably the equivalent of this facility. The first one that I'm going to talk about here was done right on their campus, because it wasn't hard enough to build a net zero house at no extra cost. We wanted to see if we could build one on campus and move it to its final location and see if we could do that for cheap too. We didn't. So like I said, constructed right on St. Don't have any real monitoring yet. Had about a 2-year display period on that one at St. We just recently moved it to its final location late last year, and the people I believe just moved in here, I want to say in the last month, so we don't really have any data on how the house is actually performing yet. Fairly simple two-story layout. I'll show a picture here in a bit. No attached garage in that one, it's a detached garage, partly to do with having to move it. Had a pretty high-pitched roof for solar exposure. A lot of the design there, of course, was constrained by that the fact that we had to try and transport that house later, so that put a lot of design constraints on it. For the envelope, we kind of learned a few lessons, at least by that point in time, from Discovery 3. So we went with a single-walled structural insulated panel, which is R44, which is still a pretty high rating. One layer, though. Did R85 ceiling insulation. Tried something kind of funky there, too. We tried to do the ceiling out of the structural insulated panels and then blow in more insulation on top of that. That also did not work out cheap or easy to move. We would definitely not do that again. Below the slab, R20 rigid insulation, kind of cut back to a more reasonable number there. At this point, we're pretty standard with the triple glaze, Krypton-filled windows. Renewable energy, similar size to the Discovery 3 house, grid-tied system. For the solar thermal system, we did something a little different. There's a few different ways that you can do solar thermal systems. One is, like I talked about with the flat plate collectors, and you literally just run some sort of heating liquid or whatever through and heat it up and put it through a heat exchanger. The other is an evacuated tube collector, which I'm not exactly sure how they work, but they work differently. And the point is, we tried some of the evacuated tube one on this one. We actually were able to do was incorporate all the railing on the house and turn that into the evacuated tube collector, which was kind of neat. On that one, we went with 360 gallons of insulated storage capacity for water, so even more than we did on the one before that. And then we'll get into why that was a galactically bad idea. So anyways, that was that house. I wasn't really involved in 4 and 5, so I don't know a lot about those ones. So these are really quick summaries on those just to show how we're moving forward and kind of get closer to that goal. So this Discovery 5, we're still working on it now with State on site. Homeowners actually moved in though, but there's a lot of stuff that still isn't done. The basement, the landscape in the rear attached garage, the cistern and stuff that I'm going to get into. This one here is one of our business partners in Avalon, and Calgary's moving into this one with his wife. Discovery 3 is also our president and general manager's house in Red Deer, so I'll get into how we know a bit more about that. So this one here, again, the electric tankless water heater, tied into solar thermal storage. It's becoming a recurring theme there. Again, we used a fan coil in this one for space heating, as well as doing radiant slab heating and domestic water, all tied in with that same system. Very similar to Discovery 3 that way. Ventilation, again, nothing terribly weird here. Same as we did in Discovery 3 and 4, just the HRV with the ECM motor that we've now sort of made a standard for our stuff. And then the controls and sensors and stuff like that to make sure it comes on when it needs to be. Again, on this one, partly due to the fact it was built on campus, we wanted to run it, and partly just because we were still zeroed in on this no natural gas idea. We got rid of that. Did the CFL bulbs. Actually, there was about 10% LED bulbs in that one too, but move on actually past that. That's kind of what it looked like. Here's a picture of the Discovery 5 house in concept. I've got some off of the presentation showing it what it looks like when it's done. You can see by this one, it's a lot more modern looking of a design. That's because this one's actually an infill, so it's kind of fit into the neighborhood there. This created some more design challenges as far as the solar goes. As you can see, it's a really flat roof. One of the things as a builder when we're looking at trying to incorporate this kind of technology into all our homes is that we don't often have a lot of choice on lot selection, orientation, things like that. So we can't always depend that we're going to have a nice south exposure for solar. So we're experimenting with doing some really flat roof stuff where no matter what your lot orientation is or your surrounding area, you're going to take advantage of that higher summer sun angle and see what you can do with that. So that's what we're starting to play around with a little bit here. I've already talked about a lot of this stuff already. For the envelope here, we moved away from the structural insulated panels that worked out to be not very cost effective and not as easy to work with as we were hoping. So we're trying to, again, get the cost down and get to something a bit more conventional. So we did a relatively traditional wall system where it was a double 2x4 wall offset, similar to what Cam was showing on that Riverdale house in Edmonton. But on the outside, we did 4 inches of the spray foam, and on the inside cavity, we did 3.5 inches of a rock solid mineral wool bad insulation. 11 inches of the spray foam in the ceiling, which is R75, again a really high level there. 4 inches on the interior of the foundation walls. Other than that, it was pretty traditional. And at this point, what's our standard with the under slab installation of R20 and the triple glaze windows. PV system on this one's going to be our biggest yet, which is 11 kilowatts. Now that's not all up and running yet because some of that's going to be on the detached garage. It's not there yet. And we're also trying a combination of 2 different types of PV systems. Again, trying to figure out which one works better with that really flat angle. Don't have any answers on which one's going to work better there yet. For the solar thermal on this one, we actually did a solar thermal chimney where all the plate collectors and evacuated tube collectors are all on a chimney running up front, west and south side of the house. Other than that, and we've got the amount of storage down to 120 gallons, and I'll get into a little bit why that is later. This one we got a little bit smarter, went back to natural gas. We're doing a natural gas boiler that's supplemented by the solar thermal. So that supplies the domestic hot water and the radiant slab heating throughout the house. Additionally, the domestic water heating is supplemented by a drain water heat recovery unit. For those of you that don't know what that is, it's basically you take the water that's going down the drains of your showers mostly is where it gets collected, and it uses the heat from that water going through a heat exchanger again to heat the incoming cold water that's going into your heating devices. So it works a lot like the HRV but with water basically. Standard ventilation that we've been doing. This one here we did a lot more LED lighting. It's becoming a bit more accessible now, both in terms of the bulbs and the fixtures. We did some, obviously, the high ultra efficiency appliances, some automated lighting, some base load control systems, very similar to what Cam was talking about with those smart switches. Water conservation, we're really trying something really aggressive on this one. This is sort of at the pushing of SAIT because they just want to do a lot of research on these systems. Not fully installed or operational yet, but it's going to involve a 14,000 liter underground cistern. It's going to use a combination of green roof technology, charcoal filters, UV filters to filter the roof runoff water. It's all going to get stored there, and it's going to be used for not only irrigation, but also it's going to be doing all the gray water in the house, so that would be water to your laundry, water to your toilets, things like that. As well as there's something I'll get into called the living wall in the house, which is basically just a big wall of plants with, it's like hydroponics for really green people. It's a big wall of plants, we got some water and stuff running through there, some UV lights, and it helps with the air quality. Of course, it's taking the carbon dioxide out and putting the oxygen in the house. We're also trying some experiments where we're growing food in the living wall, so trying to get back to that whole sustainability thing. Don't really have the final Energuide rating on that yet. We think it's going to be about 1.5 air changes, again, based on some preliminary testing that we've done. Pretty complicated design, again, tough to get that air change rate down. Talked about the living wall. The balcony off the master suite's called what's got a green roof. I don't know if anybody's familiar with that, but basically it's like growing grass on your roof, or in this case it's your deck floor, so it's like grass, but it's got a subterranean mat that protects it and collects the water, and we use that to actually filter the rainwater, taking a lot of those organics and minerals, stuff like that, and it looks really cool. This is very similar to what Cam showed on one of the other houses. So on the left side, you'll see sort of all the computer modeled usages of what they anticipated we would use in the house, and then on the right side, you'll see the computer modeled modeling of what we're going to produce with the systems that we put on the house. Okay, so this is just a quick little graph of that predicted output of the PV power system versus the actual output, which you'll actually notice it was really close. The first year, that's that sort of beigey, greeny, ugly sage color, we produced about 10,500 kilowatt hours, and we modeled to produce on average a year about 9,500. So we overproduced that year, which is great. Next 2 years, you can see we're a little lower, and that's to be expected. I mean, there's a lot of dependency on how the climate's going to work. If you have snow stuck on the panels, things like that. But by and large, and we've monitored it again since this period, and we're really close to what we should be producing. So by and large, the computer modeling is really good at predicting how much power you're going to be able to produce with these systems. Pretty basic stuff. You just have to know the sun angle, pitch of the roof, your average amount of sunlight, stuff like that. What they're not so good at predicting is how much the houses are actually going to use in energy. So the homeowners, they took possession in June 2009. Like I said, it's a business partner of mine. He's also my neighbor. I live in the house 2 doors down. And I can tell you, just from knowing him and his passion, very conservative couple. Him and his wife, and when they moved in, they had a one son, and they've since had a daughter. So the computer modeled family that they use for the modeling is 2 adults and 2 children, so they emulate that quite well. On top of that, they're very conservative. They don't entertain a lot. They have one TV in the house, which I think is pretty rare these days. One computer, it's a Mac. So power smart. Very, very conservative is the point I'm trying to get across here. They're not energy hogs, and that's important when you start seeing some of these numbers. So for the first year, he moved in around June 30th, 2009. The total PV reduction, like I talked about, was in that right range. It was 9,300. It's a bit different because it's June to June instead of September to September, but that's verified by both the meter and the inverter readings, the exact same number. Total power consumption was 13,865, so almost 14,000 kilowatts. So it's a negative balance of about 4.5 kilowatt hours. We're supposed to be at 0, being a net zero house and all. So as you can tell, we're a little off there. Following year, and this is the year he had the second kid, which I think plays into it. There you can see we produced again a similar amount, a little less, not as nice of a year, but the consumption jumped up to 17,600 for a negative balance of 8.92 kilowatts an hour. In my house, which has none of this stuff, it's very efficient, but I don't have any renewables. I use less than that 8.9 kilowatts a year, and it's a bigger house. So the home model is net zero energy. We got our label, did all the cool stuff. All the modeling showed we should have been net zero. So why did we not do that? So there's a number of reasons for that. Some of them I've touched on. Some of it is some of the stuff that the homeowner Jonas, he's my partner. He did change some stuff that was not modeled in. Those appliances I talked about, the laundry, the custom range. He got rid of those. To be honest, they're not functional for a family with 2 kids. I don't know if any of you have kids, but you can't do 1 load of laundry a day that's really small. It doesn't work. So they got rid of that. Well, some efficient appliances still, some front-loading ones. If you've ever tried to cook in a microwave instead of an oven, it doesn't work real well, so they got rid of that as well. That jumped up the consumption a bit. So the thing we did is, because of, this all kind of ties back to design, but because we got rid of that basement, we had to make up some of those spaces. So of course we've got a mechanical room on the main floor, and that takes up some space that you would otherwise have. And so we tried to make up for those spaces in other ways. And one of the things that we did is we added a mud room as you come into the house, which sort of created this sort of like an air chamber, so that you come in, you don't have your front door open and then the air going out. We thought that was a great idea, which it was, but we didn't put a front closet in there because we didn't have space for it. So when he moved in, he decided, wow, this mudroom makes a great front closet. You walk in this big mudroom, except for it was really, really cold all the time. They had all their stuff in there, their coats, their boots, their dog food, stuff like that. So they said, oh, we'll just heat it. So they threw an electric heater in there. That's about 600 watts an hour at 24 hours a day, about 5 months a year. So that alone added about 2.2 kilowatt hours a year, just that change. And something that you couldn't really blame them for because there was really nowhere else to put your stuff. So the design constraints, like I talked about, leading to those behaviors that you kind of had to deal with. Solar thermal, this is sort of a big one. Riverdale learned it as well with their big system. Kim kind of touched on it too, but so the computer modeling, when they do this, when they come out to this 0 number, what they do is they look at all the energy you're going to produce in a year and what you're supposed to consume, and they want to make those equal 0. In theory, that works good if you could use all that energy, but what happens with solar thermal, when you have a whole bunch of storage and all this capacity, is probably about 80% of that is wasted. And the reason why is because half the year when you're producing most of that heat, you don't need any heat in the house. So like May to September-ish. So you're producing the most of your heat then, and you have nothing to do with that heat. So you're putting it in these super insulated tanks, hoping you can save it until November when you need it, which anybody who knows any thermodynamics knows that's not ever going to happen. So instead what we ended up doing was superheating the upstairs of that house. And the reason we were heating the upstairs is because we had no basement, so we had to put all this mechanical equipment upstairs where you don't want the heat. And the other thing that happens when you do that is you got to pay energy to pump that heat down so that the system doesn't overheat. We had 3 of those panels blow up, and we've replaced pumps 4 times because they overheat so much. And that's what happens when you have 165 square feet of collector and only so much hot water, and you can only keep up so fast. We've since rectified that problem by making some modifications, but we've probably spent about 10 grand fixing the system since we put it in. And on top of that, we're using all that PV that we're producing in the summer is being used to run those pumps to pump that heat down under the ground. Long and short of that was we really oversized the system. It's a really simple system. It works really well if you can use the heat. But the key thing that we learned there was to size the solar thermal system so that you can use all the energy that you're going to produce. Because anything that you make it bigger over that, you're going to be paying both to pump it down. It's going to cause you problems, and you're paying a lot of money to put that system on in the first place. Computer modeling made some pretty questionable assumptions regarding the real-life use of a home by its occupants. It modeled, when I was looking at the modeling, that HRV running something like, I don't know, 10 minutes an hour or something like that. That thing runs constantly. The reason it runs constantly is because of that CO2 sensor. When you have people in the house breathing and it's that airtight of a house, it does pick that up, and it does have to run almost constantly, especially with no fresh air. So that alone added a lot to the load. Other thing it really falls down on is the space heating stuff that he was talking about. In these demonstration homes, when you're not using them, like when you don't live in them, yeah, you can heat them with 4 toasters. But as soon as you live in it, what happens is you go out of your door like 10 times a day, maybe 20 times a day. You're opening and closing that door a lot. Your wife doesn't maybe like it hot in the room at night, so she opens the window, so there goes your air changes. And that's when it's -30 out, because she's got hot flashes or whatever. Your teenage daughter sneaking out the window over here. There's all these things that happen in real life. And they do happen. And so you start using the home like you actually use a home, and they don't model in for the fact that you might have some people over for dinner one night, or it's even, or that you might run the furnace at all in summer when it gets cool and you decide to cool it down at night. Things like that. The other thing they don't model is cooling the house. So they take a house like this and they say, well, it's so well insulated, you've done all these things, you're not going to need to cool the house. Well, that's bullshit. And the reason why is because you've made this like super awesome insulated box, and you've got all these windows on the south for passive solar gain in the winter, forgetting that it also is going to heat up in the summer. If you remember to close all those insulated shutters that we have, it works great. But it turns out people don't like to live in pitch black darkness. They actually like to have the light in their house. So those don't get shut all the time, so the house heats up. So what you got to do, you got to put in some air conditioning. Well, air conditioning uses up a lot of power, as it turns out. So those are the kinds of things that the modeling doesn't show. The basement elimination was retarded. The reason it was retarded is it's really cheap to finish your basement. It's like $40 a square foot to finish a basement in Red Deer, say. Like $200 a square feet to build a second floor. So that was not the best use. On top of that, when you build a basement, the walls are a full 8 or 9 feet high, whatever you do. When we go up doing this weird half combo design thing that we did, we have like 4-foot walls upstairs, so half the space that you have there you can't even really use because it doesn't have full ceiling height, so you cram closets and mechanical rooms and things like that in there, taking away a lot of your space from your bedrooms and stuff like that. Plus you spend all this money building up. Plus you moved the mechanical room from the basement to upstairs, putting all the heat in the summer from that solar collection stuff right where you don't want it, thus again increasing the need to have air conditioning. Tried some wacky stuff as well. One of the things that we looked at when we did the design charrettes was with photovoltaics. If you can get the panels to stay at a cooler temperature, they will work better. They'll run more efficient. I've seen a varying range of studies from like 5 to 15% more efficient if you can get them quite a bit cooler. So we thought, well, we're spending like 80 grand on this PV system, let's try and find a way to make it work better. And we sort of had a natural way to do that already. We could have left that alone and it would have worked great, because with that tile roof system we had, you saw it was up on strapping. So there's this like a 1-inch airspace under that whole PV roof system, and at the top we've got vents, and at the bottom we've got spaces for water to run out in case it gets in there. So you've got this natural thermodynamic cycle of air moving in from the bottom up the top and creating basically a draft under there, cooling them. But that wasn't good enough, so we decided we should run some ducts under there too. Now, because we have these trusses every 12 inches, and because of this weird roof design that we have so that we can make living space, we had to run this big giant plenum all along the peak of the roof in the garage and the main thing, and at every truss space we had like a little intake. So we ended up with, I believe it was 52 of these different intakes running into a main plenum with a big inline ECM fan, and every one of these joints had to be sealed with a mastic sealant to make sure it was airtight so that the air didn't get in the house. And the idea was to suck the air out from that space, thus cooling it down, and then we thought what we would do is take that air and we would dump it underground through these like, we buried in the ground these insulated like weaving tile type things. We thought we would dump it down to the ground, heat up the ground, and in the winter we could like take the heat out of the ground and heat up the house. It's gonna be awesome. So it was like 20 grand to put this duct system in, and that's because it was a lot of labor to seal all this stuff. And so what we started doing after we got the house going was testing to see how the PV worked with and without it. Didn't make one lick of difference. But yeah, we disconnected it since then, which is good because it turns out when we buried the weeping tiles under the ground, when we backfilled, we crushed them, so we couldn't dump the heat down there anyways. Also, it wasn't insulated because we were going under 12 inches of insulation, so I don't know how we thought we were going to keep the heat there, but that's what we thought. So 20 grand wasted there, that didn't help. Excessive insulation, we really did go overboard in the insulation. Cam did talk about that. There does come a point of sort of cost optimization and where there's a point of no return. Where that number is it's a gray area. It's not an exact. What I can tell you is that it's not R85 or R72 in the walls, and it's not R20. And where we're at today, and I'll get into that, is we're at about R30 or so in the walls, R20 under our slabs, and about R60 in the ceiling. And we've kind of went on both sides of that. I really feel that's, at least for us, you can do that conventionally, you can do that at a reasonable cost. By reasonable, I mean in a way that you don't even really tell your clients what it costs to do that, you just do it and make that part of your standard. I already talked about oversizing the solar system. Big one here, natural gas versus electricity. Okay, so when I did the analysis on this was about 3 or 4 years ago, and at that point gas was more and electricity was less. So whatever I say here is like double that now. Because I believe in Alberta right now, natural gas is, I don't know the rate, somebody here probably knows, but electricity off the grid is about 15 cents a kilowatt. When I did this, it was like 8 or 9 cents a kilowatt. And at that time, to take one unit of energy from electricity versus 1 unit of energy from natural gas would cost you about 5 times as much to buy the electricity off the grid as it would the natural gas for that heat. This sort of ties into that geothermal argument from earlier too. The way geothermal system gets its efficiency is it takes 1 unit of energy, uses a heat pump, turns it into 3 units of energy, which is great. Unless you're paying 5 times more for the energy that you're using to run the heat pump, which you are, because it's electricity. So it will never make sense in a heating alone application, ever. If you're cooling, it makes sense because you're using electricity to cool anyways, and you're getting the efficiency back that way. So that's one of the reasons that we don't use any geothermal in this stuff. But as far as actually heating the house as a backup system with us using electricity for that tank, we're now paying, like I said at the time, 5 times as much for the energy to do the backup heating as we would have had we used natural gas, and we're putting in those complicated systems. So the house is very expensive to run. In addition to all those other things that we've done, even though it's a net zero house, it costs more to run than my traditionally heated but well insulated and well built house. So where we're at today with like progressing towards our goals with all of our homes, that we do incorporate all these things that we learned. So this is not a bad thing that all these things went wrong. Other than we lost 200 grand on the house, that sucked. Except for Jonas, because he made 200 grand on it. Other than that, we've learned a lot and incorporated that into our homes. So our standard building envelopes, all our homes now, triple glazed windows, we use the spray foam insulation in a 2x6 wall, nothing too weird there, so it's pretty basic. But it's about R30-ish. We have the insulation under the slab in all the homes. We use R60 combination of insulations in all our ceilings, really traditional. And keep in mind, when we do homes, we sell these, like we do, like I said, 50 to 60 homes in Red Deer and probably about 100 in Calgary. We market some of the stuff that we do, but we don't say how much more we pay. We compete on the same market, so we're selling them at market prices. And we're doing all these things, and we found a way to get there doing all these things without really charging any more for it, or without having to tell people we charge more for it, really. And they will buy it if they think the house is better built. I was talking to some realtors over there earlier, and they mentioned that people really won't pay more for energy efficiency, and it's true, they won't, unless you can show them that they're saving that same money right now. And you have to keep in mind that 90% of people who buy houses aren't paying cash; they are doing a mortgage type thing. And if you can show them that in the first month, you'll either not spend any more and have a better house, or you'll less, then they'll do it. If you tell them they have to spend $1 more, they won't do it. That's the honest answer to that question. And I know because I have to sell and build houses. So keep in mind, all these things that we're doing, we're selling at market cost. Durability, that's one thing people will pay a little bit more for, just because they that's something that they can see, they can sort of conceptualize. So we focus on that. We've actually partnered up with Mike Holmes, and all our homes are built through his Homes on Homes program. And that's the big thing that he focuses on, is the durability and building up proper building science, that kind of stuff. So we don't use any vinyl siding. We use all the composite cement HardiePlex siding. We've got a rain screen on all our homes. We've got lifetime rated shingles on all the homes. We use treated lumber that's treated against mold, fire, things like that, moisture, all that kind of stuff. All of that is very important, like Cam talked about, with regards to sustainability. We build homes to last 150 years, not to last 25 years. And a lot of the homes out there definitely are built to last 25 years. Energy efficiency, where we're at, we use 100% CFL bulbs on everything. We only use Energy Star appliances on everything. We're moving towards LED lighting. There's still some applications where that doesn't work really well yet. I think, we do the drain water heat recovery. We do that in all our homes now. The water conservation's the big one that we focus on here for education. Everything that we build is mostly condos, townhouse condo units, and some single-family custom stuff. We will not put in an irrigation system, and we will not advise people to water their lawn. The reason why is that you do not have to. You don't need to do all the xeriscaping. All that xeriscaping I talked about, that's like $50,000 of landscaping on those houses. You don't have to do that. You can put down sod and don't water it. You know why? Because it'll live just fine. It just won't be green. It's not supposed to be green. We do not live in the Amazon. We live in the prairies, and it's not supposed to look green. If you want your grass to look green, then you don't want to be an environmentalist. You don't want to care about water conservation. I don't care how you do it. If you put a 14,000 liter cistern under your yard or whatever, you're not supposed to have green grass here. And so on all that stuff, we just have it written into our bylaws that you are not allowed to irrigate your lawn. Renewable energy, that's something that we haven't really done because that's the expensive component. All our homes at this point are standard homes. The ones that we sell at market price are EnerGuide 86, which is, you remember from that slide, is really high up the scale. And that's what we can sell at market price. At this point, we can't really incorporate renewable and sell it at market price, and that's what we're trying to do with our standard homes. As far as design goes, Cam touched on that a bit too. It's about keeping it simple. A lot of the costs in that D3 house came about from trying crazy stuff and doing weird things with designs. The reason we have basements in Canada is because you have to get below the frost. So even if you don't do a basement, you're going to spend all the money that you would otherwise spend on a basement to give you the frost protection, get below the frost, all that kind of stuff. That's why we came up with basements in the first place. We're trying to use, make efficient use of space that had to be there. So getting rid of a basement, not a good idea in our climate. Keeping the roof design really simple, or at least the ceiling design. The roof's less important on efficiency, but the ceiling design is really important to try and insulate things properly, minimize the square footage. You do need a lot of ceiling insulation. You talked a little bit about the heel heights of trusses. We go with 18-inch heel heights in all our trusses just to accommodate cheap insulation. Like you can do R60 with blown-in insulation. You don't need to go with spray foam or anything if you allow the space for it. So design is a big one for us. And then the other thing is the houses themselves, and this kind of gets into what's needed for us to meet our goals and for housing to get where it needs to go, and that's a kind of a shift in consumer demand. If you throw enough money at anything, you can make it net zero. So you can build a 5,000 square foot house with all the bells and whistles, make it net zero if you want to throw 200 grand on renewables. That's not really fixing any problems. Where we really need to get to, as far as that goes, is a shift in consumer demand towards simpler, more basic housing. Like the wartime houses, they were all like, 900 square foot bungalows, something like that. People live just fine. And they had bigger families. So now we've got everybody with, on average, I think, it's like single family homes are over 2,000 square feet, and at least in Alberta, brand new ones. And that's not counting in condos and stuff like that. But that can't continue and then expect to have sustainable housing. We need some government and public support of renewable energy technologies. Right now, in other parts of the world, other parts of the country even, for that matter, there's a lot of incentives and stuff for doing renewable energies on your home, particularly PV. There's places in Ontario and in Europe where they'll pay you more for the power you put in to the grid than you pay to take it off the grid. That's just simply not the case here. And the real cost of energy is artificially low here, of conventional energy. A lot of it is subsidized in different ways. They're not being charged for the damage they are doing to the environment and to the healthcare system. So the real cost of those energies aren't really being realized. People talk about the cost of energy going up, but in reality it's quite cheap, especially gas. Natural gas is another one I kind of touched on. It is very clean burning. I know it sounds wrong when you're thinking of these sustainable homes to try and use something that you're burning and consider that sustainable, but when you look at where the electricity comes from, in the prairies in particular, it's primarily from burning coal, which is a whole lot worse than burning natural gas. It burns a lot less worse, and you have all the transmission losses. And like I said, you're damaging the environment far more using the electricity that you think that you're doing a better job with than you are if you just burn the natural gas, which burns really clean, produces carbon dioxide and water vapor basically. So that's one thing. Now, natural gas is not a long-term sustainable solution, but it'll make our resources last a lot longer if we focus on heating things with things that are efficient now while we work on these other things. Need some real scientific advances in areas of not just the efficiency of the renewables, even the most efficient renewables right now for PV. I think you're getting 15 to 20% efficiency out of those PV panels. That'll come, it always does. Energy storage is the big one. Kind of touched on it with the solar thermal stuff a little bit, but with solar thermal you have all this heat, all this solar energy you can take in the summer, but you got nothing to do with it. Heat's handy in the winter when you need it, not so handy in the summer when you don't. Heat's very difficult to store as well. It's, again, basic thermodynamics. If you try and hold it somewhere, it's going to go to where there's no heat. So you need to find better ways to store electricity because the battery systems available today simply are not going to cut it. They're worse for the environment than the electricity you would burn, probably just with the acids and such. As well as incredibly expensive, take up a lot of space, maintenance intensive, all that stuff. So we could probably solve a lot of the energy stuff just by having some miraculous invention somewhere in the area of energy storage. And again, who knows where and when that'll come. As far as us meeting our goals, are we going to do that in 3 years? I don't know the answer to that. A lot of that's going to depend on, I guess, how you define net zero. One way we're looking at it is if we can do all the heating in the house with natural gas and then produce more electricity than we use, offsetting the amount of carbon that would have been used by that same amount of electricity burned in a coal plant, maybe we've met our goal. And that's something that we think maybe we can achieve in the next 3 years. At least that's what we're targeting. But it'll certainly help if we get a little bit of support from the energy industry. We are working with some of those guys too. There's some really cool programs where they're doing point-of-use PV systems on house where the companies like MJEAC and the utility providers are actually buying the system, putting it on your house and renting it back to the owner while they reap the benefits of that electricity. That's a great start. If they would do more of that. Again, right now it's a bit of a cost to the consumer to do that in Alberta at least, because I think it still does cost you a bit more per month to do that. Very reasonable amount, but it does cost more. Whereas in other places they're doing that and you can actually make money doing it just because they desperately need to add more power to the grid. So stuff like that would all help, and I guess that's where we're at. So, questions? None? Okay, good. You.
There's a lot of talk about air changes and air sealing.
Yep.
Are you using poly for that vapor barrier?
We've over the sort of course of the evolution of those houses, we've went from that to now, like I said, our standard is actually to use the polyurethane spray foam, or the 2-panel closed cell spray foam, I should say. So when we do that, we don't use poly, just because you don't need it, because it is an air and a vapor barrier as well. If I was in Calgary, I think our sister company is using a combination of the spray foam and mineral wool, and they still use the poly on the inside. But that's more of the way the Calgary municipality interprets the building code. It doesn't really need to be done. But it can be done. We've gotten below 1 air change just by using poly.
Just a two-part question. Have you done or are you considering projects outside of Alberta?
We're a really small company, honestly. So the answer is right now, no. I know our sister company in Calgary is doing work with the Homes program on the I think it's the Riverwalk project in Okotoks, which is a pretty big one, and that's about as far away as we're considering right now.
Okay, and the other part is the projects that you're doing, either single detached or condominium, do you go into existing traditionally designed subdivisions for infill, or is this in new areas where you can
both.
orient the solar and all that?
Both. That Discovery 5, like I kind of showed there, it's an infill, so it's an existing area. And we have done a few other infills, both in Red Deer and Calgary, or major renovations anyways. And I'm doing one, or starting one in Red Deer here in a month. It's an infill as well. What I'm focusing on mostly right now is actually take whole areas and do our whole own community of multifamily stuff, like townhouses, duplexes, stuff like that.
Who determines the interguided rating system? How do they determine?
Who determines it? Well, there's a modeling program. The question was who determines the interguide rating system. There's a modeling program that ultimately shoots out that number, and it's called HOT 2000. Although, are these in HOT 3000 yet, Cam?
Not yet.
They're between HOT 2000 and HOT 3000, which is sort of owned and operated and by an outfit called Enercam, which is a subsidiary of the government. Cam, Enercam.
Natural Resources.
Natural Resources Canada. Sorry, so they determine that basically, and there's a lot of interpretation when you do that modeling. A lot is left up to. I can do the modeling myself, and I can come up with a different number than another guy who models and interprets things a little bit differently. So there's a little room for movement on those. Not a lot. I mean, not unless you do something really wacky.
On the roof sections where you're putting in your solar hot water collectors or your photovoltaic, do you have to use above normal traditional roofing materials, or do you eliminate that?
No, you could use standard roofing materials if you wanted. Like I said,
the reason I'm saying this is if you're building a new house,
yeah,
and you didn't have to put shingles down,
yeah,
you'd be saving that money.
Oh no, you still have to run a membrane and all that kind of stuff under it. Any money you'd save doing that, you'd spend on the membrane and the proper flashing and all that kind of stuff. There's
one of the pictures, it looked like it was just being laid on top of the sheathing.
Yeah, on some of the solar thermals we've installed it right over top of the existing shingles, and some we've worked around it, but either way you're spending about the same.
Yeah, I was just wondering about the grey water system.
Okay.
Is it standard across Canada, or is it?
Actually, the grey water is a tricky one. I know, maybe Philip probably knows more in Toronto. I think in Toronto they allow what's called the BRAC system, which is a system where there's like one big sort of collection tank in the basement that collects from all the different grey water sources and then uses that water to feed toilets and laundry and things like that. In Red Deer, or in Alberta at least, we're not allowed to use that yet. They won't let us. They're not referencing a building code to the best of my knowledge. They just don't feel it's safe to potentially contaminate the water supply. There's a lot that can go wrong, but they are concerned about that. So the system we got away with so far is just using the basin feeding the toilet. Really single system, no opportunity for contamination. We had to do a backwater valve on the other side of it. The chest house, the other one that was done in Red Deer he showed you, they put the backwater system and they were not allowed to use it. The city wouldn't let them. So I think that depends on the municipality.
You mentioned rock solid mineral.
Mm-hmm.
Well, and did you say it was good or bad? I wasn't sure.
Oh, it's great. It's there's nothing wrong with rock salt. It's a really good sound insulator. We use it on a lot of our party walls on multifamilies for duplexes, townhouses, stuff like that. It's inert. It doesn't soak up moisture, so it's great that way. It can't mold. It's got better sound and thermal characteristics than traditional fiberglass. So it's good that way. It is still prone to the issues that you'd have with any kind of insulation that's based on using air as an insulator, so air still moves through it. Still doesn't give you an air or a vapor barrier like a spray foam or something like that, but a much superior product than fiberglass.
What kind of partnership did you have with SAIT?
Those were the ones done in Calgary, and I wasn't really involved other than as a consultant, but on the first one, there's a gentleman there by the name of David Silburn, and he sort of was the project manager. He's with SAIT. He's in charge of their advanced research and building and stuff. I don't know his title, but something like that. And he was the project manager. He was also able to arrange a lot of grants and stuff through various programs, educational programs and government funds, as well as solicit a lot of donations from suppliers and stuff like that, being with them. And like I said, we actually built it on their campus, so that was a big part of it as well. Their students helped with some of the trades and labor, like some of the install. Not all of it, not the commissioning, but they did some of the install.
Okay.
Cool. Looks like lunchtime. All right, sit.
I just wanted to thank Trevor for his candid description of their evolution, and the term Discovery Homes is really what they're doing. They're really turning over things and seeing what works and what doesn't at considerable expense. So thank you very much for sharing that. Appreciate it.
Just a couple announcements. We'll reconvene at 1:45, and we have some interesting sessions. I'm inviting, I know Friday afternoon there's no classes for SciAS students here, but invite you to come on back. And also to note in your program tonight as well at 7:30 we're having a special presentation where we're having some young people come in and talk about their careers and what they're doing. It's a company out of Chrono that has a solar energy installation company. Troy Tilbury, who's one of your instructors, and his wife are coming to talk about their design initiatives. Sarah McRaven, who's here as well, is going to be talking about what she's up to. And Eric DeWall at the back, Eric Penner DeWall, is going to be talking about a house he built in Regina, a roughly 600 square foot house using recycled materials. A company out of Regina, Zoot Pictures, is just in the final stages of making a documentary on that, and he'll be sharing a trailer on that film tonight. So that takes place at 7:30 here as well. So don't be afraid to come back this afternoon. Check out the program as well for tomorrow, and we'll reconvene at 1:45 right here. Thank you very much.